This video is about the logical operators and, not, and are. Just quickly recall that a proposition is a statement that can be true or false, and a compound proposition is a proposition built by combining simpler ones. And here's a non-trivial thing we talked about in the last video, that our goal is to determine the truth value of compound propositions, not simple ones, using the truth value of each of the simple components. So that's what we're trying to do in logic. And so in this video, we'll figure out how to deal with compound propositions, or at least we will start the process. You need to introduce some notation. So we'll let PQR stand for propositions. Okay, with that, let us get going. So we're going to first we want to figure out how to build compound propositions, and we build compound propositions using something called logical operators. And, are, not, and implies. So if I take two propositions P and Q, and I can create a compound propositions P and Q, for example. This video we will focus on these three. Let's start with and. The logical symbol for this is an upside down V. Okay, so P and Q stands for P and Q. Oops, it's pronounced and, so it's just P and Q. And what can we say about P and Q? It's exactly the same as you would expect from English. P and Q is true if both P, Q are true, and is false otherwise. No surprises here, and I'll do examples in a minute. Then we have or. Here the symbol is just a V, capital V, and so this stands for P or Q. Now here there is a little bit of subtlety. Remember that logic is supposed to be very precise, so we assign a very precise meaning to or. And P or Q is true if either P or Q or both are true. Okay, so it's yeah, I will not say more. Is false otherwise. So the extra bit that you have to remember is that it's allowed for both of them to be true. Sometimes in English, when we say something or something, we mean like exactly one of them, but here in logic, we allow for both of them to be simultaneously true. Okay, and then finally, not. Here the symbol is, I don't know how to say it, it's like an L, but it's written, it's like flipped, so it's a flipped capital L. And so not P, so this stands for not P. And not means just opposite or negation. And so not P is true if P is false. It's false otherwise. Very, very intuitive operators, and or not. The only subtle thing is with or. Okay, now let's do some examples. Let's keep on doing the thing we were doing last video. So 2 plus 2 equals 4. Suppose we have P is this proposition, Q is the proposition 2 plus 2 equals 5. Okay, and let's take, yeah, I think this is enough. So let's start with not, because that is the easiest one. So let's determine truth values of, let's do P and Q. Oops, I said that we'll start with not. So let's start with not P, not Q, P and Q, and P or Q. All right, so now we want to determine the truth value of these compound propositions. So what we'll do is we'll start with the truth value of the individual propositions. So P is the proposition that P 2 plus 2 equals 4. And because this is true, we will assign P the truth value 2. And we'll assign Q is 2 plus 2 equals 5, which is false. So Q gets the truth value false. Just T stands for true and F stands for false. And now I can use our definitions to figure out what not P, not Q, and all of these are. So first we'll start with not P. Because P is true and not is negation, this is negating the truth, and so this is false. Then we look at not Q. Because Q is false and not is negating, this becomes true. Then we have P and Q. Now here, remember that and is true precisely when both the things are simultaneously true. Here P is true, but Q is false. And so this thing becomes false. And finally with or requires at least one of the two things to be true. Both can be true if needed. But here we know that P is true. And so this forces this to be true. And so that's how you determine the truth value of propositions involving not, and or. Okay. It's very simple. There's no complication here. Now I'm going to tell you a structure that logicians use to record the information of these truth values. So this is called a truth table. And what it is a way to record truth values of compound propositions for all possible truth values of the components. And it'll become very clear from the example. So let's start with truth table for P and Q. All right, so I want to create a truth table for the compound proposition P and Q. And what I need to do is I look at all the component propositions. So here they are P and Q. And so I'll start by putting them like that. So these are the components. And from this, I'm building P and Q. All right. Then what I need to do is I need to take all the possible truth values of P and Q together. So P can be true or false, and Q can be true or false. But I want to make sure that I take into account all the possible ways in which they can be true or false. So there are 4 such ways. P can be true, Q can be true. So that's, then P can be true, but Q can be false. Or Q can be false and P can be true. Or the last one is this. So what I've done is I've written all the possible pairs of truth and false. Okay, and now by the way, the way and is defined, it's true precisely when both are true. And so this is the only case where I'll get a true, and for all other cases, I get false. And so this table, called the truth table, is encoding the fact that P and Q is true only when both P and Q are true. That's it. Then truth table for P or Q. Again, I'll start by looking at each of the components. So that is P, Q, and I'll put P or Q on the side. Then I'll again put the truth values of P's and Q's in pairs, in all possible pairs. So I'll have true, 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 false, false, false. And now the way OR is defined, we just need one of the two things to be true. So in this case, that happens, oops. So in this case, that happens here, here, and here. And so I can encode this information as true, 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 and false. So this is a truth table for P or Q. So truth tables are built for compound propositions. And finally, I can build a truth table for not. And here, there is only one component proposition. It's not the case that I'm combining two of them. I'm just using one. So all I have is P. And I'll just put not P here. And now P can take either true or false. So this truth table is very easy. I'll have either true or false. And when P is true, not P is false. So this becomes false. This becomes true. And so this is the truth table for not P. That's it. That is what truth tables are. In the next video, I'll explain how to build truth tables for longer compound propositions. Okay. And one last thing I want to say before we end this video, that is, why do we write truth tables? Like, what is the use of truth tables? Truth tables are not useful for exactly determining the truth value of a particular proposition. For example, when I did this question, I never needed to know the truth table. I can just figure out the truth value by hand. So then why build this entire enormous truth table? And this is useful truth tables are useful for determining a logical equivalence of two statements. So if I give you two logical compound propositions, which might look different like superficially, but if you build their truth tables, you might see that they're actually the same. So let me give you an example, which we'll come to in the next few videos. For example, this is something called De Morgan's laws. If you do not of P or Q, then turns out this is the same as not P and not Q. And you can prove this using truth tables. So that's all I want to say. Let me just say that without writing anything, that it takes a little effort to convert from English, like compound statements in English, to logic, because English, as we know, is a little imprecise, whereas logic needs to use either and or not or implies and nothing more. But it's not hard, and there are some examples in the book that you can see, which will guide you through the process. And that's all about compound propositions and truth tables.